Good morning, that is good afternoon.
Good afternoon. So good morning and afternoon.
Yes, 5 o'clock.
It's 5 o'clock for you. Okay, we can start. Well, welcome to today's session of AMP. The first speaker of the session is Julien Ricaud from IMAS UNAM, and he will talk about spectral stability in the nonlinear Dirac equation with solar type nonlinearity. So, Julien, please.
Thank you, Ricardo. So first, I would like to thank you, Ricardo, and all the organizers for the invitation. And so, yes, as you said, I will speak about spectral stability for a Dirac equation. So let me right now start. Oh, so it's a joint work with some colleagues in Chile. So Tonko Aldunate, Edgardo Stockmeyer, and Hanne van den Bosch. And you can find here the reference. I mean, my talk will be based on this paper that we published last year. So what does it work with? Yes. So I'm announcing Dirac equation, but I will start with Schrödinger. So why is this? Because I want to give some context for the results that I will present, and maybe also because part of the audience is more acquaintance with Schrödinger equation. So and it allows to put in perspective the results, I think. So after that, I will present the solar model that I will consider, then the non-results, and I will continue with our result, and of course, some open questions. There are many. So first, as I said, let's look at the Schrödinger equation. So it's a nonlinear Schrödinger equation, which is, I mean, as you all know, and the nonlinearity is here. So it's f, it's a function. I mean, it has some property, but it's not very important at the moment. And we are also interested more precisely on the stability of solitary waves. So what are solitary waves? We already see it in this nice conference. So it's solution of this form. So if you plug it in, you just make easy computation, and you end up that your phi zero that I will abusively call the solitary wave. That's the profile, spatial profile. Sorry, it has to satisfy this equation. So of course, before talking about stability of anything, you better have the existence of such solution. So for the existence, it's known for quite a long time now. I mean, it's the reference that I put here from Berezetsky and Lyons. And in particular, so it's known in any dimension, but since I will focus later mainly on the one-dimension case, I'm talking about the one-dimension case where we have if and only if characterization in 1D. And just to give an example, because it will be also the kind of nonlinearity that I will look at, it's a power nonlinearity. Then for Schrödinger case, if you consider this nonlinearity, then you have, I mean, the existence is only if W is negative. So just to say that we know that it exists, and then we can study actually the stability. So I will be interested mainly in the linear stability, so spectral stability. So you have to look at the linearization operator, which is just you put some perturbation on your solution, you plug it in, and then you see what is the linearized operator that you obtain. So I write it here, it's here. So a big disclaimer for some of you who are used with this kind of problems. I have no minus here. It's not a mistake. It's because I put an I here. So just a convention, because I prefer to have that stability when everything is real, when otherwise it's when everything is purely imaginary. So it's a personal preference. So no worries, there is no sign mistake. It's because I put an I here. And so the linearized operator is, as you may know, it's just anti-diagonal with an operator which is usually called L minus, which has this form, which is actually exactly this operator that appears here. That's solitary waves solves. And you have the other anti-diagonal operator, which is just the same L minus some another nonlinearity, which is here. Okay, so this is what you have, and what I wanted to say. Yeah, so here I said everything I wanted, and then just to go quickly, because that's not the main part of the talk, what is spectral stability? So again, due to my convention here, the spectral stability means, I mean, it's characterized by the fact that the imaginary part of any eigenvalue has to be non-positive. Okay? Usually, if you don't make these conventions, maybe that you find strange, it will be that the real part has to be non-positive, but I take, I have the other convention. Okay, and so I don't want, I mean, there is a lot of literature about that, and so I cite some of them here, and obviously I am far from citing everyone who should be, but I have not that many places here, so I had to condense. And so once you have spectral stability, usually for Schrödinger, it can, I mean, it's at least the first step, and sometimes it allows you to characterize the orbital stability, and even in some special cases, asymptotic stability. So that's the general framework that I would want to do for Dirac, is to first address the first step of spectral stability. So, so now I will present some result on the, I mean, what is known about the spectrum of this linearized operator for Schrödinger. And again, I do it because I will put it in perspective after for Dirac. So as you may know, and as we already see in the conference, so you have part of the spectrum which will be the essential spectrum. So you can look at the essential spectrum of these two operators. They have the same essential spectrum, which is minus omega plus infinity. And for H, so your linearized operator, it's just take it and you switch it like this. And so it gives you minus infinity omega and minus omega plus infinity. Remember, for Schrödinger, omega is negative. So that's why you have a gap if omega is non-zero. Okay, so it's an essential spectrum, and some nice properties that helps you to solve quite, let's say, quickly the spectral stability for Schrödinger is that, so first, of course, as I said, phi 0 solves, I mean, it's a solution, I mean, it's a ground state for L minus. And you also have that the spatial derivative of L plus is also a ground state, no, sorry, so spatial derivative of phi 0, sorry, is a ground state for L plus. So you have two zero eigenvalues. And a very important property is that actually L minus is positive on the orthogonal of the ground state. Sorry. And finally, L minus has only one negative eigenvalue. So it has phi zero prime is a zero eigenvector, and you have only one eigenvalue that is negative. These are two very nice properties. Why? Because with this, you can actually quite, I mean, it's a direct computation. You can show that any eigenvalue of H has to be on the complex axis. So remember, I want to prove that any eigenvalue has to be of, has to have a non-positive imaginary part. So now I know that the only thing that can happen is any eigenvalue has to be purely real or purely imaginary. So I already eliminate most of the complex planes that could be bad. So this is a nice property that, unfortunately, we will not have for Dirac, but that's one. And then the next thing that you do usually for Schrödinger case is that you have what is called the Vakitov-Kolokolov criterion, or I think sometimes it's only called the Kolokolov criterion, which tells you that actually if you look at the derivative in omega of the mass of the solitary waves to the square, if this is non-positive, then actually you cannot, you have only purely real eigenvalues. I recall I am in my convention where I flip everything. So what's happening here is that you see they can be only on the axis, the eigenvalues for any omega. So now imagine you know that for some omegas, they are purely real or your eigenvalues. This criteria, what it tells you actually is that you cannot have any eigenvalues that pass through 0. So if everybody is real and nobody can pass through 0, nobody can go to the imaginary axis. And so, I mean, with the end, I mean, it's the end demonstration, it's the sketch of proof, it's a vague idea, it's how you do it. So, and that's what I will try to somehow replicate for Dirac. Okay. And so to give again an idea, to compare later with Dirac, is that if you are in 1D and you take a power nonlinearity like this, and for any positive powers, then actually your Vakitov-Kolokolov criterion is exactly equivalent to say that kappa is less or equal to 2. So you see, you have less or equal to 2. So here we have, so it's a quintic, because here you have 2, here you have 2 by 2, and you multiply by. So it's a quintic Schrödinger equation, which is a critical case. So here for Schrödinger, so it was a very quick wrap-up about Schrödinger, and now I will present you and pass to Dirac, the main object of my talk. So what is the model? So the model looks similar, but some way. So first, let me clarify, I'm only talking about 1D here. I will explain later why. Mainly because it's easier, I mean, it's more accessible, let's say. So the equation is here, that's the Dirac equation that we are looking. What do we have? We have the one-dimensional Dirac operator with mass m, so which I wrote here. So I took the convention to take it with sigma 2 and sigma 3. You could actually make any choice, and you can pass from one convention to another by some unitary transform, so it's no restriction to fix them. And so I have my one-dimensional massive Dirac operator here, and I have my nonlinearity. So it's called solar type because actually we are looking at the parameter inside the nonlinearity f is of this form. So what is important in this model is that you see I have here, I chose sigma 2 here, I chose sigma 3 here, and here the Police matrix that is here must be the same as this one, must be the same as the mass in the massive Dirac operator, which makes that this nonlinearity is mass-like. I mean, that's one important feature of my model. I need to have this. Other than that, I could put any polymatrix here as long as these 3 ones are the same. And that this one is a distinct one. And otherwise, you can do what you want. So what is this modeling? So it was proposed in 38 by Ivanenko to represent the dynamic of spinors that were self-interacting through a mass-like potential. So in all of this paper, if I remember well, they are all in 3D, but so this is a 1D equivalent model. Then it was reused by Finkelstein, Lelevier, and Ruderman in nice papers, and Heisenberg, basing himself on this paper, used it to propose a unified theory of elementary particles. And then later, so the name is Soler because in 1970, Soler just used it again, this model to study the extended nucleons, self-interacting extended nucleons. And finally, maybe some of you know the model as the Gross-Nove model. So the Gross-Nove model is exactly this model in 1D for which you take that the nonlinearity f is just the identity. So just to give some references. So now we do the same as for Schrödinger. The first step is to be sure that you have existence of solitary waves if you want to study their stability, of course. So let me first say that in 3D, it's known since 86, and in 2D also, it's just an extension of the 3D case. But as far as I know, for the 1D case, the first proof was in 2012. by Ricaud and Komesh, if I'm not wrong. And so let me present a little bit in detail. So you need some assumption on F, of course, for it, but they are quite generic. And since later in my talk, I will focus on this power nonlinearity, that you can think only about this nonlinearity if you want. It's also the generic assumptions that I need. So under this generic assumption, you have existence of solitary waves for all omegas between 0 and m. So the first difference with Schrödinger, where it was a negative omega, here it's omega between 0 and m. And then, of course, similarly, you have some operator L0 that phi 0 is ground state of. So the operator is just here. It's the same. I mean, it's just actually just this one where you have this omega that comes from the derivative when the derivative hits the exponential. And you have some nice properties. So this phi 0 decays exponentially. You know the rate. You can choose it real valued. It's two components. So it has two component phi 0. So let me just clarify this compared to Schrödinger. Now it's a two component. And don't ask me why it's VU. The literature said VU and not UV. So I do the same to not change too much. And so the first component can be is even, and you can choose it to be positive at 0, and the second component U is odd. And finally, you can check, it's not a trivial, but you can check that actually the parameter that appears here, the parameter of F, which depend on X, of course, it's always positive. So it's an important property, and so all these properties you can find them in. I mean, of course, for 2 and 3D and above dimensions above, it was known, as I said, since '86, and for 1D, it was you can find in this paper and then in the book of Boussaïd and Komesh. Okay, then let me just show how the solution looks like, just to give an idea. So here I have V. And here I have U, and if I'm not saying anything wrong, the greener is when omega is close to 0, and the yellow, when it's more and more yellow and even orange, it's when omega approaches m. So that's the kind of, so it's really nice solution. So let me say now that one word about why do I study specifically 1D is because in 1D, actually, you have explicit solutions, I mean, explicit formulas for phi 0. So in terms of arc, tangent, hyperbolic tangent, etc. So you have explicit formula, so it will help to make computation later. So now we have to look at the linearized operator. So it's the same process as in Schrödinger. We put a perturbation to our solution, to our solitary waves. I take the same convention, so that's why I have no minus here, and I write my solution, my linear operator in that way. So it's again anti-diagonal with L0, which is the one of which phi 0 is a ground set that appears here, and here you have L0 minus 2 something as before, as for Schrödinger, and this what I call Q is here. So it can look complicated, but actually it's quite nice. Well, nice. It's the derivative of F applied to these parameters that I just told you that it was positive, always positive. And you have this, this matrix. And it's a non-negative operator, self-adjoint. So it looks quite nice. And so why is it non-negative? Because one important property that one has to assume, which was one of the generic assumptions that I mentioned before, is that F prime must be positive on R plus. So that's why it goes well. And so now, as the question that I ask myself is about the spectral stability. So again, what I would like to prove is that the imaginary part of any eigenvalue is non-positive. So let's say here. Okay. So as for Schrödinger, let me present what is known. I mean, before our work, what was known and what is some, let's say for most of them, some direct observations. One comment about all my graphics, all my graphic representation, when you have something in greenish like this, it means that I know that it's here in the spectrum. Where you have nothing like gray, it's I don't know. And later when you will have some pinky salmon color, it's I know absence, that there is nothing. Okay, so just to say that I'm not saying that the spectrum is this. I'm saying that what I know about the spectrum. So remember, my linearized operator is H, it's anti-diagonal, and I mean, the better I know L0 and L2, more likely I will know things about H. So I study both of them. So here you have the spectrum of H, and here it's the spectrum of L0 parameterized by omega. So vertically it's omega, and if you take like the intersection of this representation with a straight line, horizontal straight line, it will give you, sorry, the spectrum of L0 at that omega. So this is just to summarize what is said here. So this essential spectrum of L2, FL0 are the same as the one of the massive Dirac operator. So it goes from minus infinity to from minus infinity to here, which is minus m minus omega. Then you have a gap, and then it starts back at m minus omega to plus infinity. So this is an essential spectrum. And for H, again, it goes from minus infinity to minus m plus omega, and from m minus omega to plus infinity. So of course, here I stopped it here, but it should go all the way along here and here too. Again, you have two simple eigenvalues. This is generic, so you have phi 0 is an eigenvalue associated to, an eigenvector associated to the eigenvalue 0 for L0. Its spatial derivative is 1 for L2. So nice property that we did not have for Schrödinger that we have here is that actually if you take sigma 1 phi 0, which is just you flip the component V and U, then it is an eigenvalue of L0 for the it's an eigenfunction again of L0 for the eigenvalue minus 2 omega, which is this one, this straight line here. So this one was the vertical straight one, this one, and this one is the eigenfunction associated to the eigenvalue here, which is minus 2 omega. And the other nice property is that actually sigma 1 phi 0 is in the kernel of Q. So actually sigma 1 phi 0 is also an eigenvector for minus 2 omega for L, what I call L2 here. So it's a very stable eigenvalue. And of course, what I should mention here is that contrarily to Schrödinger, we do not have the property that L0 is positive on the orthogonal of phi 0. Of course, it's a Dirac operator, so you have negative spectrum. So you cannot have anything like this, which is bad, which is a difficulty for us. The other nice properties actually, so okay, I say that the spectrum of L0 is symmetric with respect to minus omega, which is here, okay? So say otherwise, if you consider L0 plus omega, it will be a very nice symmetric spectrum. But more importantly, that the spectrum of H is symmetric with respect to each of the axes of the real, a purely imaginary axis of the complex plane. So which means that for the spectral stability, remember I said that I wanted it so the spectral stability was that any eigenvalue has only non-positive imaginary part, but the spectrum is symmetric with the real axis. So now the spectral stability corresponds to having a purely real spectrum. So that's very important. So now my goal the ultimate goal would be that to prove that the spectrum of H is purely real. Again, let me recall that I have my convention that spectral stability is not, I have switched it compared to the standard convention, let's say. So now, up to now was what was nice. Now what is not nice, not nice, what brings some difficulty and make it interesting is that actually, so to compare with Schrödinger, I said that for Schrödinger, the eigenvalue were on the axis of the complex plane. Here we do not have this because, as I told you, one way at least to prove it, and quite quickly, is to use the fact that L0 is strictly positive on the orthogonal of phi 0. Since we do not have here, then this direct implication, this property that you can derive quite quickly for Schrödinger, fails here, or at least I don't know any way to prove it directly. So that's the first thing that we are missing compared to Schrödinger. And the other one is that anyway, even if you add it, the Vakitov-Kolokolov criterion is not clear. It's not clear that you have it for in the Dirac case, I mean, in the solar model. So, and actually, if you remember, for Schrödinger said that the Vakitov-Kolokolov criterion was that if this quantity was less or equal to 0, then you could conclude. Here in this paper by Berkolaiko, Komesh, and Suktayev, sorry, they actually prove that if it was equal to 0, you could still have some eigenvalues that pass through 0 and goes to the imaginary axis. So just to say that the two nice part of the proof for Schrödinger fails here. And so what is known about spectral stability now, what was known before our work? So as far as I know, everything that was known for the solar model was only for the power nonlinearity. So partly why is that is I told you that in 1D we knew exactly the formula for phi 0 for the solitary waves. I was missing something actually. We know it for solar model in 1D if the nonlinearity of this form. And that's part of why most of the results are known for this. And so what were the known results? As far as I know, there were only two, which are the two that I said here, I'm mentioning here, sorry. So it proves that if P is strictly bigger than 2, then in the non-relativistic limit, sorry, which means that when omega goes to M, so when omega goes to M, when omega is very close to M, it has been proved in this paper by Komesh, Guan, and Gustafsson that actually for any P strictly bigger than 2, you have spectral instability. So just to put it in perspective, this P equal to limit corresponds exactly to what I said for Schrödinger, which was that it was called kappa. At the time was kappa equal to, where you have it was a threshold between having stability or not for Schrödinger. And the other result that is known is that for P strictly bigger than 1 but less or equal than 2, so 2 included, you have actually spectral stability, again, only in the non-relativistic limit. So there are great results, but I mean, it's quite specific, and actually there was not, I would say that, I would dare to say that there is not a lot known about it. And finally, let me mention about the results also that you have some numerical results about P equal 1. And for P equal 1, it's conjecture that it should be spectrally stable for any omega. Even so, you have some debates in the literature about for small omegas if the numerics are valid or not. So let me not enter in that. But so it's conjecture to be stable. So this was what was known when we tried to look at this problem with my collaborators, and what were we able to do now. So as I said, I mean, you see you have H that is like this on diagonal. So one guess is that the better you know L0 and L2, the better chance you have to be able to, you will be able to say something about H. So we started by looking at L0 and trying to say something. So the first thing that we were able to prove that is useful is that actually you really have a gap here. You have no eigenvalues here in this pinky area. So remember what I presented before about the non-result was exactly the same thing for L0 without the pinky region, which means that what was known to be present in the spectrum, what we prove is that actually you have nobody here. So, and in that sense, we can call these two eigenvalue here, the eigenfunction associated to these two eigenvalue, which are 0 and minus 2 omega, we call it ground state because I mean in some way you have nobody in between. So this is valid for any F. I mean any F for which you have existence of solitary waves. And additionally for L2 we prove something similar, which we prove that nobody was also in this gap between minus 2 omega and 0. Remember that now 0, the eigenvalue 0, as the eigenvector associated to it is the phi 0 prime. It's not the same. The eigenfunction for minus 2 omega here and here is the same, but the one associated to 0 is not the same here and here. And so as I was saying, we are able to prove that there is nobody here except for only one eigenvalue. So in some sense, this is similar to, it's the equivalent as for Schrödinger for L0 when we said, okay, it's positive on the orthogonal of phi 0. This property to have nobody here is a corresponding property. And the property to have only one eigenvalue in this gap is the one corresponding for Schrödinger to saying and to have that L plus, has only one negative eigenvalue. So we prove the corresponding properties for Dirac. And so maybe if I have time, I think so. So quickly, the idea of the proof for it, what it is. So you see, you consider an eigenvalue of L0. So I'll write it as an eigenvalue of L0 plus omega because it makes the computation simpler. You just make some computation and you can prove actually that it's equivalent to have this eigenvalue equation as a matrix. I put M, so M is a mass-like potential, let's say, mass-like potential. So it's really the one from the massive Dirac plus my nonlinearity, so minus my nonlinearity. So now you square it. So you square this operator, and it's a diagonal operator with two Schrödinger operators, which are these two operators. So one with minus, one with plus. And what is nice now is that you can notice that actually V plus U and V minus U are eigenfunction of this. I mean, each of them are an eigenfunction of this Schrödinger operator, and they are both associated to the same eigenvalue, which is omega square, and they are strictly positive. So now by Sturm oscillation theorem, then you know that you have no eigenvalue below them. And so L0 plus omega to the square has no eigenvalue below omega square, and then you can recover so that L0 plus omega has no eigenvalue between minus omega and plus omega, and then it gives you that L0 has no eigenvalue between minus 2 omega and 0. So that's the first part of the theorem, which is here. Okay, and for L2, so this proof was quite, simple computations and some nice observation. The other one relies on some tools, which are namely the tools that gives you that characterize the eigenvalue of a self-adjoint operator with a gap in the essential spectrum. So I'm mentioning 3 papers for them, so which are the 3 ones, which are Dolbo, Esteban, and Serre, in 2 of them, and one more recent by Schimmer, Slovej, and Tokus. So this one was an extension, let's say, to non-self-adjoint case, and also, if I remember well, I don't know if it's one of these 2 papers when there might be a little gap in the proof, if I remember well. But okay, so what is the idea of the proof? So it's twofold. So first, we prove that actually all the eigenvalue of L2, and it's the same for L0, are simple, and they are continuous in omega. So if you look at them as branches, depending on omega, they are continuous. Then what we do is that we use this, let's abstract theorem that characterizes eigenvalues. We do it only for here for power nonlinearity, and we prove actually that again where we are in the non-relativistic limit, very close to when omega is very close to m. Then actually with this we can not only characterize, but we have an expansion of the eigenvalue with accordingly to the parameter omega. And so we can prove that very near to omega equal m, we have only one negative eigenvalue that is strictly above minus 2 omega. So we know that here we have only one, and now we know that the branches of eigenvalue are continuous in omega, so we can continue, so they go, and they are simple, so they can never cross, these branches here can never cross minus 2 omega, neither the branch 0. So it cannot go out of here. And since you have only one eigenvalue near when omega is near m, it means that in all this area, you have only one eigenvalue. So that's how we prove it. And so again, this relies, or proof relies heavily on the fact that it's power like nonlinearity, so we know explicit formula for the thing, and so we can have explicit expansions of the branches of eigenvalues. Okay. So the next step after knowing better L0 and L2 is to say something about H mu. About H. So remember, it was called H, and before it was a 2 here. So one thing that we did that was, I would say, novelty of our paper is that we say, okay, let's, instead of being stuck with just the real H, let's study it by parameterizing this this parameter here, calling it mu. So why do we do that? We do that because if you take mu equals 0, so you have L0 here and L0 here, now your operator is self-adjoint, and so you have purely real spectrum, which is what we want to prove for the case mu equal 2. So the idea is to say, okay, we know for mu equals 0 that we have the property we want. Can we propagate it from mu equals 0 to mu equal 2? So that was our approach. Because, okay, let me say that as far as I know, in the literature, all the approaches were done by making omega vary. It's omega what was the parameter that was varying, and us, we fix omega and we make mu vary. So, okay, I'm changing my operator, so I better have some nice properties. So first we have basically we have the same properties that we had for L0, L2, and H. So namely that sigma 1 phi 0 is an eigenvalue associated to -2 omega. So -2 omega is an eigenvalue that is totally stable with respect to mu. The essential spectrum does not move, neither for L mu or H mu compared to before, and we still have the symmetry of H mu, of the spectrum of H mu. So we have all what we want. So we still have to prove that H mu has a purely real spectrum in order to prove spectral stability. And so we come to our main theorem, which is a conditional one, which goes like this. So you take omega between 0 and m to have a solitary waves, of course. And you assume that f first is such that you have existence of solitary waves, but also is such that L2 has a single eigenvalue in -2 omega 0. Remember, it's something that I know how to prove in some cases. I just did it. And you assume also that you have the Vakitov-Kolokotov criterion, like this. Then under these two assumptions, we're able to prove that, as I wrote it, for any mu in 0, 2, the algebraic multiplicity of 0 as an eigenvalue of H mu is equal to 2. So what I'm saying here is that, remember, I already know that H mu has two eigenvalue. Sorry, no. H0, yes, H0, H2 have two eigenvalues that are stuck here at 0, which are the one associated to phi 0, 0 and 0, phi 0 prime. And now what I'm saying is that basically with the end, I'm saying that nobody can know the eigenvalue will be able to come and pass through 0 and go to the axis. So I'm preventing eigenvalue that would reach the purely imaginary axis, actually, to come from the real axis. If you want to have said otherwise, yeah, no, let me not say, I will say it after, because now it's a corollary, actually, is that the corollary tells you that if in addition, you can exclude some part of which we will be able to do, of course, if you are able to exclude the presence of eigenvalue if part of the complex plane, namely the cone that is close to the purely imaginary axis. So you have the imaginary axis. If you can eliminate anyone that is in this cone, and of course below also, then you will be able to prove that there is actually no purely imaginary eigenvalues for H2. So why I am focusing on purely imaginary eigenvalues? Well, two reasons. The pragmatic one is that it's something that we are able to do. The other thing is that, as far as I know, being numerically or analytically, any unstable eigenvalues that has been found for the solar model was purely imaginary eigenvalues. So maybe let me go back here, and I did not comment on that on the non-results, that here, the spectral instability, actually, it's proved by finding a purely imaginary eigenvalue in this regime. So again, so the only known instability for this model are purely imaginary eigenvalues. And so that's why we focused on excluding them. It will not prove spectral stability, but at least it will, it's reducing the chance for it to be unstable. Okay, so we have time, I think so. So quickly, the idea of the proof for this theorem is just first, so the first property, you can prove that it's equivalent to saying, okay, let me go back to the, because I think it's better with this. So you see, you start with, no, sorry, no, I will not do it like this. It will, so with L mu, yes. So the thing is that not that L2 not having any eigenvalue in minus 2 omega 0. Yes, sorry, I'm very sorry. Yes, that was a nice thing to do. You see, for L0, you know that you have nobody here, and you have 0 that is an eigenvalue. Actually, what happens when you start? So here I put mu. When you start to turn on mu from 0 and start to increase, this eigenvalue will start to enter this cap. It will bend into this cap like we see. So it will start to go to the left. And you see, at first you have no other eigenvalues. Well, sorry, we don't know if there are eigenvalues here, but for any eigenvalue to reach 0, it has to come from the left because Q is non-negative. You have a minus, so when you turn mu, it has to, the eigenvalue are moving to the left. And so what we are saying here is that if we know that L2 has only one eigenvalue here, and since we know that 0, you have also 0 just arrived here, what we are saying is that just before mu reaching 2, this eigenvalue was not there, but it was a little bit bended here inside. So basically, that's what we are saying here. We prove it, of course, but that's what it's saying with the end. And then this will allow you to say that this is well defined, this function of mu. And then after you prove that this h actually is non-decreasing, then you use the Vakhitov-Kolokolov criterion, because now H2 is, you prove by n that H2 is exactly half of what appears in the Vakhitov-Kolokolov criterion. And so if you assume that this is non-positive, then you can prove that actually the algebraic multiplicity of 0 as an eigenvalue of h mu, it being bigger or equal than 3, is equivalent to h mu equals 0. But this you know, okay. So here you have to be subtle. If this is strictly negative, then it's done, because this is strictly not negative and h is non-decreasing, so you have it. You have that this cannot be 0. And if it's equal to 0, you have to work a little more, but you can still prove it. So that's the kind of, that's why, so let me say that's why we need our two assumptions, because our proof of this requires both of them. And then now, okay, it's nice to have a conditional theorem with two things, but when is it working now? So here I'm presenting where we are able to exclude purely imaginary eigenvalues. Again, that's the only eigenvalues that at the moment are known when you have instability. That's the only unstable eigenvalues that are known at the moment. So this is presented for poor nonlinearity still. And what I am saying is so that H2 has no purely imaginary eigenvalue, except 0, of course, when we are in the intersection of these two areas. So when we are here, we prove that there are no purely imaginary eigenvalues. So what are these two areas? These two areas are, so for the green one is the one corresponding to the Vakhitov-Kolokolov criterion. So that's the area where we are able to prove by end that the Vakhitov-Kolokolov criterion holds. How do we do it? As I said, in 1D and for power-like nonlinearity, we know explicitly the formula for phi 0. So we know the explicit formula for this. So we just compute this and we find by n some criteria on p and omega for which we know that it's less or equal than 0. It gives us this area. So one thing to remark is that this is the limit here where it changes in the non-relativistic limit when omega goes to m, it's p equal 2, which is exactly where the non-results are known. Remember that I said that it was known for the letters that when you are really omega close to M, so at the top here of the graph, for P strictly bigger than 2, it's even known that you have instability, spectral instability. And that below up to 1, it's known that you have stability. Us here, we are not proving really stability, we are proving that there are no purely imaginary eigenvalues. But just to say that this 2 here, this change here, this threshold here, is in accordance with the non-results. And the violet one here, purple-violet one, is the area corresponding to having this bond. You know, it was the extra assumptions that I did in my corollary to exclude purely imaginary eigenvalues. And so when you do it, you have it like it gives you this area, and so the intersection of these two areas is where we can exclude purely imaginary eigenvalues. So I'm not sure I have really the time for this. So just a quick idea how to prove this bond. You start by algebraic computation. So you take an eigenvalue of h mu, which is not on the axis. So that's really a non-zero real part and a non-zero imaginary part. And then, I mean, you make some algebraic computation. Let me go quick. You can prove this kind of relations. You know also that psi1, what I call psi1, is actually so psi1 is the first component of psi, psi2 is the second component of psi. You can prove that it's orthogonal to the ground state, so this will be well defined. It's also orthogonal to the eigenfunction associated to -2 omega. And so you decompose it and you still work algebraically, and you find some expression, exact expression for real part of the square. And then here you make some lower bound on the numerator, some upper bound on the denominator, and then you can work out some conditions. Let's say. So that's the kind of proof we do. And so again, we excluded purely imaginary eigenvalue. So now let me conclude with this. Conclude our result with this representation, which is a sketch of what we are at now. So as I told you, the ultimate goal is to prove that the spectrum of H2 is purely real. We do not have it, but we excluded a large part of the bad things that could happen. So again, we have in green the non-spectrum with the essential spectrum here and the non-eigenvalues here. And so what we did also was first to, you know, with this condition that I just presented here, which is that one, actually, you can take it bigger than 0, but you can also decide that you want it to be bigger than some parameters, than omega. So you want it to be bigger than m minus omega. Actually, you can make it as close as you want as 2 omega, as plus 2 omega. This, I mean, you can take this lower bound as close as you want to plus 2 omega. You cannot go above, but you can go as close to it. Of course, the more you ask it to be close to 2 omega, the smaller your region here, your purple region here will be. But you can for it. And so the sketch is this, is that we are able to exclude any eigenvalue in this parabola here. So delimited by these two parabolas here. You can exclude eigenvalue here that are here, but not on the imaginary axis. Then thanks to it and to our conditional results, we also exclude the purely imaginary eigenvalues for some parameters, of course. And then finally, on top, it's just, I mean, a quick computation. You can prove that the imaginary part of the eigenvalue cannot grow too fast with mu when mu goes from 0 to 2, and so you have a problem. So just to say again, we would like to prove that everything is Salmon, which means no eigenvalues except the real axis. We do not have this, but we make some progress and we eliminate it. In particular, we eliminated the possibility to have purely imaginary eigenvalue, which again was the only unstable eigenvalues that are known up to now, as far as I know, at least. And so let me conclude with open problems. So of course, we would like to make the graphs that I just present you all Salmon pinky, which would be proof that you have no eigenvalues. I don't know what I put this because that should be not here. Okay, so it's true for this. If we could prove, as in Schrödinger, by an argument, independent argument, that the eigenvalues are only on the axis, we would be done. But ultimately, we would want to prove that it's only on real. So other thing that we would like to do very well is that to go away from the power-like nonlinearity. Remember, most of what are presented and what is known in the literature about the the solar model is when you take F to be a power nonlinearity. So we would like to go beyond that, and the first step would be to prove these properties that will prove the power nonlinearity, which is crucial for us, and which is saying that there is only one eigenvalue in -2 omega 0 for L2. So we think it should be true as long as F behaves like power nonlinearity near 0. We think that's the only thing that is needed, but up to now we are unable to prove that. And of course, the next question, if we obtain spectral stability, would be to study orbital and asymptotic stability. Let me mention that as far as I know, there is no result telling you, okay, if I assume spectral stability, then I could prove orbital stability for the solar model. As far as I know, there is not even that, so this would have been to be done also. And finally, well, going to higher dimension, because I mean, life is not only one-dimensional. And here, basically everything would be, I mean, not everything. A lot of things are still to be done, at least if we want to follow our way of proving things, because one of the main problem here is that in dimension 2 and 3, we have no explicit formula for the ground state phi 0, and our proof relies on having those formulas. So a lot of open problems, and I think I'm finished, and I thank you for your attention.
Well, thanks, Julien, for this very nice talk. Are there any questions? Well, I have a question.
Yes.
If I recall properly, you mentioned that in some cases orbital stability does imply asymptotic stability. Could you elaborate on that?
Well, I made also sketchy about Schrödinger because I'm not a specialist, and I mean, with additional assumption, and it's his paper of Kukania, and if I remember well, there was 11 technical assumption to be able to have it. So I think it was really I think he found all the ad hoc assumption to make it possible.
Mm-hmm.
So maybe I should have emphasized that it was not small additional assumption. I mean, it's strong assumption that they do to have it.
Right. So then, so far, spectral stability is not known for the solar.
No, except in, as I said, except in the non-relativistic case. So except in those two cases, if you really say, okay, I send omega to M, you know that you have some omega 0 above which you will have spectral instability if P is bigger than 2, which correspond to the Schrödinger quantic. P equal 2 correspond to the Schrödinger quantic. And you also have spectral stability if you are between 1 and 2. And strictly bigger than 1. And if I remember well, they cannot go below 1, not even at 1. Because what they do actually is they say, okay, I take the non-relativistic limit, and in this limit, I can relate the spectrum of my Dirac operator with the one of the Schrödinger operator. Because the limiting operator is a Schrödinger operator, the one that I presented. And the thing that these relations that they can find, it fails, it does not hold anymore if P is 1 or less. So that's why they are stuck here.
But then in this case, when you go to omega, that you do have a spectral stability, is it orbital or asymptotic stability, you know?
As I tried to mention that, it's not even known because
Not even in this case.
as far as I know, there has been no work. I don't know any work, let's say like that actually go even say, okay, let's assume spectral stability. Can I find anything about orbital? No, I don't know any work proving orbital.
Not even in the non-relativistic limit.
No.
Omega goes to M.
No.
Okay, well, thank you. Any other question? Well, if there are no questions, we thank the speaker again.
Thank you.
And next talk is at 10:15. So it's on, well, over 20 minutes. So 10:15, it's, we reconvene then at 10:15. 10:15, sorry.
See you.